built the name.
Yes.
We all work in label object environments. We have heard this in several talks today. This means that we like to work with these kind of things. Objects that get connected in sort of complex ways. Some of us work in business applications, some of us work in development environments, but we all have to deal with these complex networks of objects interacting, sending messages among them. Things like this, like the closure that earlier mentioned earlier. But at some point, we need to take these live objects and save them away. Take them apart from our image. And then we can do that by freezing them. For instance, we can use a database, a classic database, SQL or no SQL. That means getting them flat and send it by a string, a file, or any string that we have. But then the time passes. We haven't taken those objects away from our images. They are apart, but time still goes on. And we change the scene because we work in smalltalk specifically for that, the capability of changing everything. Then our environment also changes. But those saved objects don't know that. We all have to face this problem at some point. The usual form of this we have with code objects. When you save code and later you retrieve the code that the image has changed. Now I will talk about the different phases of this problem, which is what happens when we save model objects. What we have and what we expect to find when we retrieve. Well, it's like this triangle. We have you have instances of model classes because it's your object model. You have also instances of common library classes because you need strings, you need days, you need timestamps, and so on. And of course you have references to globals because it's very hard to do anything in smalltalk without using at least a class reference. What we expect to find then when we retrieve the saved object model? We expect to find the classes that we have instances, because we saved the instances but not the classes. And those classes have changed. We expect to find the common library classes. Common library classes also change at a slower pace but change. And we expect to find the globals that we work with. Well, problems that we have. Classes could have changed their name. We identify the classes by name, and that name can be changed. It's a common refactoring. Classes can have changed their shape, because, again, it is small. We add an instance variable, we rename an instance variable, we remove instance variable. So they are all normal operations, and our saved objects don't know that. These last operations can be solved using mappings. So that's not a big problem. But also, the semantics of our classes will have changed, or just our business rules will have changed. The globals we are referencing could have unexpected values, not the values they used to have when we say, but different ones. Well, when retrieving several model objects, you cannot have name conflicts because you are not saying the names, but you can have references that are not there anymore. And most likely, you cannot solve all these problems using automatic tools. You have to intervene. Besides, the interesting part of this is, as Andres says, that it seems to work. You can have all in place. You can see no conflict, no error. It's all fine. But something may be wrong, and you can discover it. Right? Well, now concrete things. This compatibility is what we have implemented for PetroVR. PetroVR is a tool for simulation in the oil industry for business models. But the part I will focus now is the 2012. Because now we are in 2012 version, but this tool started several years ago, in 1997. Well, we cannot use now the model saved in 1997, but at least we can retrieve models and use them, of course, saved as far as 2005. So we have 7 years of fully working documentation. This is the first view of PetroVR. I will not go into detail, but it allows the users to model their oil field exploration. So we have objects of many different types representing the main object. We have reservoirs, we have facilities, we have wells, oil wells, gas wells, and we have pipelines, things like that. In numbers, a medium-sized project, which I worked when preparing this, can have 8,000 or something like that objects, in good quantity of literals, so simple objects, but also objects of more than 100 of our model classes. The same with our tiny demo projects have similar numbers. What we have to save these models in the basement, we work with this object dumper and object loader. They are very simple serializing and deserializing tools based on the original and old ideas of the binary object string like this. And as many serialization tools, they have some hooks that the programmer can use to customize the saving and retrieving of its model. One of these hooks is the damping surrogate. This one is invoked when, in the moment where we are exporting, we are about to save a model object, it will answer a different object because we want to modify the object or to get a different one to save. Why can't we do that? Because in the working objects we have many times transient objects like caches, for instances. And we don't want to save So for instance, a big map has instance variables related to the context where it is drawn. And we don't want to say that, so we produce a copy and do clearing operations to not say the parts that we don't want. It is useful to clear transient variables, as I said, and also we can take advantage of it to encode some information, because instead of saving an object, we can save a literal, an ID to retrieve it later, or a global expression. We have another hook which is kind of symmetrical with it, which is after read activate. As its name tells, it is applied after loading an object from the stream, and its intention is adapting the instance variables. It also can return it from the variable. It is used many times to reverse the effects of the previous. Here we have an example in Ferro-Saving where we can see that it makes some forced initializations of variables. This can happen, for instance, to isolate basic initialization. It is an interesting hook because one can be tempted to use it for biocompatibility. Because at the moment where it is used, it will be easy to think that we can adapt the saved objects to the current version of the system. But that would be difficult because there is no warrant about the ordering in which the objects are retrieved, so we don't know if this object is other objects to the present. Besides, it produces a kind of scattering of the adaptation behavior, because it goes object per object and class per class. And the last one, it doesn't scale well when we pass through several versions, because we start to have lots of conditional code to see if we come from version 4, then do this. If we come from version 5, then do that. Speaking about versions, there is a common problem when working with saving and retrieving models, and it's to have a reliable source of the version number of your system. We have a simple solution for VR, and it is to have one place where the current version is in one method in our code in one of the root classes. Well, the VR suite includes many different tools, and each one of them has a different kind of model objects. We have econ models, global models, multi-carrier tools, some kinds of spider and sensitivity analysis, scenarios, decision trees, contracts, portfolios, each one having a different kind of model. So we needed to think about a hierarchy of objects to read them, because each one poses a different problem. This is part of our hierarchy. And this is the schematics for reading one of these models. We read the version number, then in the stream it counts all the objects compose the model, and then we check the validity of the model. If all went well, we migrate it to the current version, which is where all adaptations are done. The reading proceeds like this, instantiating a reader and telling it to load from the stream using mappings. As I have said, mappings are a common solution for renaming instance variables or renaming classes. Well, not these mappings that are something like this. Mapping one name to another. We have an example here. Not sure if you can read, but we have two different mappings here. One of them is for a class rename, just says the old name and the new name. The other one is for an instance variable, and also does old and new name. It's very simple. And we have sets of mapping for every version where it was needed. Well, we have to do some special support on mappings because we can have complex situations a long time. We can have class A renamed to class B, then renamed to class C, so we need to provide a bridge for that. And also later we can reuse the name class A because every map wants to have a class A. Well, this is the migrating current version. For migrating the current version, after we needed a different hierarchy of migrators. Because of the same, we have several different models. The idea in the migrators is to work in a very incremental way. We have small methods of migration, each one for every version where we introduce differences. So we produce an effect like this shell picture. We start with something, apply little changes version by version, and arrive to the other side with a different version, adapted to our current version. Well, now some specific examples of code. This is real code, working code, but let me assure that no real objects were harmed. This is kind of a classic. It performs two different adaptations. The first one is business rule changes. We decided to deactivate some variable in a specific case. And the second one is more structural. We have a migration forcing every facility model to change and adapt to the current version.
The name of the method is always for the previous version, right? One incremental change.
Yeah. Yes, these are changes to migrate to 10.107 from 106. Well, we have a need here, and that is these methods should be important when possible. And that is to get some nice properties. For instance, when we are debugging this kind of migration, it is easier for the developer to restart the method and to be sure that it does not try to do the same adaptation twice. Another classic case is we have new instance variables in the class, and we save the objects of this class. Before that, we need to force the new initialization of those variables. In the current code, they get initialized in the initialized as usual. But we need to add some migration code for that. In this case, we run through the reservoirs, take the depletion plans, which are from the class I have shown before, and then check if it does not have a proper option, we initialize it. For the first part, the web results record, and in the second part, we directly set it to false. Note that we use this bar name here. It's not a program, it's low level, but we are okay with doing that in migration code because migration code is on the kitchen of our system. We can use anything if it has access. We can have changes in the representation. For instance, we have a variable set as decline for digging wells. Later we decide that instead we have a full-size object, which is an injection performance. We do this. The migration code for that goes like this. Going forward on all of the digging wells, well by well, create an injection performance for it. Configuring it, saying it goes to the well, and finally using is bar name input, set its decline. Internal changes in selectors. Well, we usually don't save the selectors, but there are some references integrated to selectors. For instance, in the column specifications for the group. Here we have a case where we have changed something to the base value, we use display value. We can do that configuration, retrieving the columns, and then changing the variable. This is a bit hard. We can require class change. Let me tell you the case. We have a facility spec of after class over here. Here we have a power plant spec as a specification for a power plant. Here we have a generator, which is a power plant that also produces steam. Later we decide that it's better model using a steam plant, which also produces power with a special converter. So here in the migration, we select the facilities that are power plant generators and change it to class to the new steam plant spec, and then do some initialization and adapt the extrusion. Yes, we can change the class of those options when needed. Well, we have some parts of the code where we decide not to use objects, but instead some symbols indicate something. Later we decide to use shorter symbols, like in this case, auto-read completions, auto-complete. We need to propagate that change in all the recompletion policies. These environments. I have spoke before about what happens when you rename variables, and also what happens when you move the variables to another object, for instance. Then you cannot use mapping. So we introduce this concept of missing variables. Here we have an example. These locations have a logical variable, which was actually defined x and y coordinates, and a physical variable that was introduced early in the design, but later we decided not to use, and was always needed. The next version, we needed to incorporate the z coordinate for the depth, and also decided to remove the unused variable, and instead of using a point and a set variable apart, we use x, y, and z directly in the locations. That's a big change. Because we needed to get the variables from the point, which is not here anymore, and that is where missing variables come. We iterate once, take the location, which is the modified object, and find in the missing variables of the location, if it is not new, of course, we can retrieve the point, because missing variables is just a dictionary where the keys are the old variable names and the values are the values. Once we have the point, the rest is straightforward. We define the x and y from the point and initialize and set the movement to 0. We have a little different example. At first, we have oil and gas fluids directly as instance variables of a reservoir. Later, we decided to have an object representing the set of fluids and the reservoir knowing this one. Oil and gas are in this. So again, we don't have any more oil and gas variables in the reservoir. They go to the missing variables. So we iterate reservoirs, retrieve the missing variables, and check for oil and gas into temporary variables, and then set them to the fluid of the reservoir. Migration issues. Well, as always, you have issues. Sometimes you need to do something like this, because you have several ways of migrating something, and all of them may be correct. So someone has to decide. For that, we introduced the migration issues. Well, they are defined in an extensive manner. The schema is very simple. You set the string, you set the potential receiver, and you set the selector that you will send to it in the case that the user chooses this option. It's like building a menu. Well, broken cards and broken objects. Sometimes, as you have seen in many of these examples, I ran through collections of objects in the model. What happens when our change is so basic that we cannot use the current iteration methods? To resolve that, we introduced the first stage where we do repair of the objects that cannot satisfy the current navigation. This is a little example. For instance, forcing and initialization of this capacity because the current iteration assumes that there is never any we have particularities of behavior. We use functional language for the user to introduce expressions like this. They are simple expressions relating to the variables to produce some results. But these expressions are in text. So integrating the text also has a different set of products because variables are represented by names. When we changed our name structure, which uniquely identifies the variables, we need to do some different migration work. we started from things like this, which is very extensive, that were only with the purpose of changing some part of the name to a different place, to a different level. It's not very interesting thing here, but noting that it evolved into general services like this one, which is also long, but much more clear because it ends renaming a collection of old names to a collection of new names. We only need to go through the objects and collect the old names that we have, transform them to the new names that we need now. Also, the variables have ranges. First, we did not take much care of this, and at a later stage, we enforced the ranges more carefully. So we needed at some versions adding ranges that were not previously defined, which is pretty easy to just insert the range. And finally, something similar happened to the variable descriptions. The variable descriptions, when the variables are calculated, should indicate clearly how they are calculated. And most of the times we add that later.
Okay, so any questions? Any question? It's obvious that the system is very complex for the number of migrations to the system. How, well, you present like 100 different migrations. How comfortable are the developers with changing something in the system, like changing the class? How comfortable are them? Because it's complex and it requires extra job to do the migration too, right?
Well, we try to feel comfortable to change anything with complete freedom, because afterwards we add the migration code. And yes, it is a little extra job, but we have a great experience doing this, and now it's pretty easy after the change to build the migration code. We have lots of examples. Many things already covered, so it's most likely that the part of the task that is adding the migration code will be 10 minutes, 15 minutes. So it's not a cost that prevents the programmer to do a change.